basically. You see light coming out. If you take a lifesaver, candy, candy is shaped like a torus, and you break it, you also see lots of sparks. So it's pretty interesting. And what happens is, I've
haven't noticed. I've never noticed.
I can't get that.
Yeah, well, it's hard to find a dark place. But yeah, take a piece of tape in a dark room and then just pull it apart, and you'll see a kind of bluish glow. And what happens is you're forming these filaments of the adhesive, of the rubber, and there's some unevenness of electrical charge. You have a little more here than here. And eventually it breaks. And when it breaks, you have 2 points really close together. And you have some charge here, opposite charge here. And because the distance is really small, you have huge electric field. The volume is small, but the electric field is enormous. Right? So you ionize the air. Right? You pull apart the molecules, they come apart.
So it's sort of, it was in dielectric medium, and then when I take off the tape, I put the charges in the air, and then it's easier to...
I think you just have 2 pieces of tape, adhesive, sticking together. Okay? And it's electrically neutral. And when you pull it apart, then you end up with kind of strands.
I see.
And it is just that the charges are unevenly distributed. And so, so eventually this guy thins, and then when it breaks, I mean, that's a really interesting thing, how things come apart. You have a singularity, it's also mathematical singularity. And then you have this very, very small separation between these 2 really sharp points. And so you have enormous electric fields. Yeah, the world is full of interesting things. There's also, Kelvin came up with this electrical generator, which is a little similar to this, uses this spontaneous separation of charge. So the idea is you take 2 tin cans. So these are just ordinary tin cans that soup comes in or something. And you solder a piece of copper wire to the can, and you make a little loop here. And you do the same thing here. Copper wire, they cannot touch, of course, loop here. And then you put an eyedropper here and here. I'm forgetting something. I'm not doing something right. And you put 2 cans down here.
When water jar with your charges? When water jar down with your charges?
Yeah, I'm trying to remember.
We have that one in physics.
No, I have the thing wrong, I think. Yeah, it goes up from here. And then you have one. There's one in physics?
Yeah, we did that. They showed that to us, the setup.
Yeah.
And then when the water jar and they start building charges and they start spark in the middle. Like after they build a certain point.
We built one at Alpha Micron one summer, but maybe that was before your time.
Yeah.
Anyway, so the idea is that you just have this story, and so imagine that a water drop is falling off here. And so it's the same kind of thing, the water drop hangs, and then at some point it has a skinny neck, and then it breaks. And suppose that there's an extra electron on the water drop. Okay, so when it comes apart, the charge distribution is not exactly perfect, and there could be either a negative or a positive charge on the water drop that falls. So suppose you have an extra electron, so the water drop falls in here. Now we have a net negative charge. It's tiny, but it's there. Okay, so then, now this water drop which is falling here kind of sees a negative charge here, so it has a positive charge because it loves the negative. And so when this drop falls, it becomes positive. Now the next guy that comes down here is going to say, oh, positive. There's going to be more negative charges down. And you can put a neon tube in between here, and it will light up. It's amazing. There's nothing there, just water. And it's a beautiful thing. It's just gorgeous. So Kelvin, it's called the Kelvin water droplet generator. So
full.
Okay. I wanted to do one more dimensional analysis example, which is to estimate the viscosity of water. I don't know what number example this is. Okay, so I want to know what it is. And again, we just want to do the same trick that we did before. We imagine somebody actually calculating somehow using complicated stuff the viscosity of water, but when he's finished, then he's going to have some equation that says mu equals something. So this is the viscosity. And so again, our job is to figure out what are the relevant quantities and how to combine them to give us something with the units of viscosity. And just like we did before, thinking about intermolecular forces and energies and things, we should be able to come up with something useful. So what are the units of viscosity? Who knows?
Velocity in it somewhere.
So this is like, this is like the problem we did with, what are the units of B or something, or mu, okay, it's a different, use a different symbol, it doesn't really say the same thing. So if you don't remember, you need to think of some equation that has viscosity in it, and then you can figure out what the units of viscosity are.
Well, the force is equals to viscosity times area times speed over the distance between the layers.
Yeah, very good, just so. So a simple way to think of viscosity is, again, imagine that you have a surface, tabletop, which cannot move. You have some stuff in between here, oil or something, and you want to exert a force so that this guy is moving with some speed v. So how much force do you have to exert? So the force, obviously, if it ain't moving, you don't need no force. So the force somehow depends on the velocity, and simplest linear case, the force is proportional to the velocity. So it goes as the velocity. And it goes with the area. The bigger this piece of wood is, the bigger force you have to have. If you have 2 pieces of wood, you need twice the force. Right? So it's pretty clear. So that's the scale as the area. And then the thicker this layer is, the less force you have to apply. That also makes sense. So and the proportionality constant is the viscosity. The more viscous the thing is, the bigger the force is. Okay. And you should all be able to convince yourself that the geometric factor is just A over D. We'll see this kind of thing a lot, but it's good to think about it, how it comes about. Why, you have to imagine 2 pieces of wood side by side, one on top of the other. Good understanding of this. Okay, so it's good so far? And then we can get the units of A to right away, because this has units of mass times acceleration. Or let me just say instead that it has units of energy divided by length. Is that okay? Energy is force times distance, so force is energy per length. And then we have eta here. And here we have velocity these guys cancel out. We have a length cubed, and we have eta as units of energy. Energy divided by length cubed times time. And energy density is, we said, was the same as pressure, right? Energy per volume is the same as pressure. So eta has units of Pascal seconds. Pressure times time, or energy density times time. Those things are discussed. Okay, so it's the first thing, then it's one of the units here. So eta has units of Pascal seconds. And of course, we can write this in terms of the 5 fundamental things as well. Okay, so now it's clear that we have to construct something that has units of energy per volume times time. Okay. So what kind of energy do we have in the picture? KT. Right, so somehow we know that viscosity is associated with things bouncing around, carrying energy, so KT is a measure of that. So the energy we have is KT. So we have KT, and now this is just the thermal energy, right? Whatever the temperature is, it's going to be this amount of KT excitation throwing the molecules around. So we have KT, okay, now we still need two things. We still need a time, and we still need a length cubed in the denominator. Okay? So here we have a length cubed, and then we need some kind of a time. All right, so what is a relevant length here? We have what? What length do we have?
Diameter of the molecule.
Yeah, that's all there is, nothing else.
And the time of relaxation.
So it's just the size of a molecule, so this is just some molecular length. And then the time, yeah, what is the time?
Relaxation.
What does that mean?
It means a molecule move and hit another molecule. The time average
Right.
of this.
Collision time. Time between collision. The
Collision.
molecules boom, 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 banging into each other, right?
Yeah.
So it's pretty much got to be collision time because we understand that this process is just these balls bouncing around.
Because also is just
Okay, so this is molecular size, molecular length, and this is collision time. Now collision time is kind of hard to estimate. What is it?
It's the distance between molecules divided by the average speed
speed.
of
Average speed of molecule. Right. Right. So just that.
average speed we can be found from E.
PBT.
Right. Absolutely. It's also related to the speed of sound. The speed of sound is essentially the speed with which the molecules move. Sound can go faster than the molecule. No reason for it to go slower. So a kind of an easy way out is just to take one of these L's over here and say this is some kind of a velocity. You know, I just put the speed of sound in, which is something we happen to know. What is the speed of sound in water?
1,000 meters per second.
What is it in air?
340
Meters a second.
Yeah,
So it's about 1,000.
Bigger.
It's about 1,000 for water.
I just guess because it should be bigger in water than in air.
It's bigger in solids, right?
Right. Sorry, yeah, right.
Okay. So we can estimate that eta is roughly speaking KT, whatever that is, divided by some L squared times 1 over the speed of sound. Okay, so let's put some numbers in. So we already said that k is 1.38 times 10 to the minus 23, and t is about 300, right? So it's something like 4 times 10 to the minus 21. Now we said that maybe 3 angstroms or something, right? So if we square that, we get 10 times 10 to the minus 20. No, 6 times 10 to the minus 20. Or L squared. And then we have the speed of sound, which is 10 to the 3. And again, we don't have to worry about units. We know that this will end up having units of Pascal seconds. Okay, and so this is roughly 1. And so here we have 10 to the minus 1, 10 to the minus 3. So we get 10 to the minus 4 Pascal seconds. Okay, and if the actual is about 10 to the minus 3. So it's not bad, given that we didn't really do anything carefully, just threw some numbers together. Okay? So in this way, you should be able to calculate all kinds of interesting physical properties of matter, electrical resistivity, all kinds of stuff, just by making these kinds of arguments. And again, the key thing always is to identify the relevant quantities. And this also says that bigger molecules are going to be more viscous. That makes sense. And if you heat things up, they will be more viscous. And that's sometimes true, but it's not always true. So, because the thermal motion gets more complicated for oils, for example. Like you have, things are less entangled at higher temperatures, so that's a more detailed model. Okay, any questions on this? So this is just about the end of the story. So the main point is that just by the simple approach, you should be able to figure out relationships between various quantities and also estimate material parameters. And so I really kind of fell in love with dimensional analysis because people can do really magical things with it. And I was telling my friend who's a theoretical physicist in Hungary how much I liked it, and he says, but did you know that you can also do problems where everybody has the same dimension? And then I thought that didn't seem likely. But it turns out that you can prove Pythagoras' theorem using dimensional analysis. That's a little surprising, right? But it's a nice proof. How many people could prove Pythagoras' theorem right now? Yeah, how many people know what it is? So that, Pythagoras' theorem just says that you have a triangle ABC, then a squared plus b squared equals c squared. Everybody knows it. The proof is not so trivial, so you might want to ask yourself, you can prove it. Okay, so the way to do this by dimensional analysis but you would think you wouldn't be able to do it, right? Because everybody has the same units. What can you do with dimensional analysis, right? But you can prove it, and the proof is really nice, and it goes like this. So we call the hypotenuse C, and then this is a right angle here, and we have 3 other angles. Let's call these alpha and beta. Now, if we specify any 2 of these quantities, one side and one angle, any 2 of these quantities, we should be in good shape, right? One side and one angle. Two sides, okay, should be able to have the answer. Two angles is not enough. But if you specify one side and one angle, then you certainly know what the triangle is, right?
Because we would like to prove, so maybe we can use beta equal to 90 degree minus alpha, and then we can use the something related to the cosine or sine in the mathematical calculation, and then we can prove it.
Well, I think the proof I propose is something like that, and the idea is that the area of this triangle must be some function of C, the hypotenuse, and one of the angles, let's say alpha. Okay? So you agree that if I tell you C and I tell you alpha, you can construct the triangle, right? And then you should be able to figure out the area. So if you know these two things, you should be able to get the area. Now the dimensional analysis part goes like this. Well, if this is an area, the right-hand side has to have units of area. So the only way that can happen is if we have a C squared up. So this must look like C squared times some other thing, and that other thing can only be some other function of alpha. Everybody happy with this? No other way. Now, at this point, I could have given you beta, and everything would still work. And if I made the same argument with beta, I would get the same expression here. So that means that this g function of alpha and that same function of beta must be equal. So I can also write this as c squared g of beta must be true. We cannot distinguish between alpha and beta. Okay, so now, and then we can say, all right, if I draw a line here, so I have another right angle there, then the area of this triangle plus that triangle must be the same as the area of the whole triangle. So that part is true, right? So we have that A1 plus A2 must equal A. So this is A1, that's A2. And then we just write down for A1, A1 must be the hypotenuse of this triangle, which is A. So we have A squared times G of beta, but G of beta is the same as G of alpha. So G of alpha. And then for this guy, again, the area is the hypotenuse squared times G of alpha. And that must be the same as the area of the original guy, which is C times G of alpha. That's right. Okay, so dimensional analysis even works to establish relations between things, all of which have the same dimension. Okay, so I thought that was just kind of a pretty problem. Okay, that's it. So that's kind of the end of the dimensional analysis story. Any questions or comments? I will not talk more about this explicitly, but I really expect you to kind of practice it, because I will give you on the midterm exam questions which are just like this. Using dimensional analysis, do something, figure out something. So really practice it, and you'll find that it's a really, really valuable tool. Okay, so the next thing is assignment 1. So let me hand this out, and you can talk about it. And Yue will help you with this. I didn't have a chance to give you a copy, Yue, but it's what we talked about. So, Yeah, there should be a copy going around that you can get.